So let's get into the actual topics today. So as we know, our buildings in timber are getting taller. It is something that essentially a lot of different builders, developers, suppliers all brag about having the biggest tall timber building. Luckily in Australia, Atlassian, I'm pretty sure it's almost topped out. It's an incredible building, 40 stories as well. So it's getting taller and taller and taller. But intuitively, we know that fire and timber burn. So it's the question mark that everyone probably watching Atlassian Tower goes up, why are we putting logs that I'll put on a fire into a building, basically? But questions well asked, but also well answered. But there's something else that happened a little while ago, and this has got nothing to do with timber, but it did spook everyone when it comes down to combustible materials and compliance. So Grenfell, it's a famous building that went up in smokes. 72 people died. The issue here was combustible cladding, not timber, and also no fire sprinklers. So without sprinklers, there's nothing to suppress the fire as well. So a lot of these things are adjacent to the timber solution and the things that actually stop the fire and going ahead. A bit closer to the home, we also had Spencer Street fire. So again, combustible cladding was an issue, and we got everyone a little bit spooked. And it's one of those things when there's a lot of uncertainty involved and you don't know the topic very well, naturally you go towards risk aversion. And I think timber got the brunt of that, particularly in the UK where the market got hurt. So understanding compliance is really critical here and knowing how to navigate things. And the first thing when it comes to compliance, this is the same across all codes essentially. What are the goals that you're trying to achieve and the functional objectives? And then how are the performance requirements achieved? Then underneath that, as I'll take you through, there's multiple pathways to achieve it. So firstly, it's life safety, firefighting prevention or intervention. They're the key things, but then also business interruption and controlling property loss and the amount of costs as well to make sure that buildings can get insured at the end of the day. So when it comes to timber buildings, there was great work put together by Forest Wood Products Australia and individually Boris Iskra. He did a lot towards this essentially and really took the industry forward to give us confidence on this. And what it meant was there was a clause in the building code entered that you can use, so even if the building code says it needs to be non-combustible, you can still use fire-protected timber, meaning you're allowed to use timber even though it's a combustible product essentially, as long as the building's not 25 meters in height, which is about 8 stories. You've got a sprinkler system, and the research shows that sprinklers pretty much do a lot of the heavy lifting. There's research in Canada to show that it doesn't matter what material the building is. If you've got sprinklers, you're pretty much totally fine. But also it needs to be non-combustible as well, and then cavity barriers and things like this. So great, it's in the building code. So closer look at the building code, there's essentially performance requirements. So what are the objectives that you're trying to achieve? And then there's 2 compliance pathway solutions. So one essentially is the performance solution and the other is the DTS. So the deemed to satisfy is a bit much like getting a cookbook, going into Marley Spoon, following a recipe. If you follow that, you're going to have a beautiful dinner because a chef has put it together. And if you follow their steps, you're great. But the other one is you can hire your own chef to cook the meal as well. And that's essentially a performance solution, that achieving the objectives of a nice, tasty, nutritious meal at the end of the day. So that's essentially one way of looking at it. So if you look at the overall functional objectives, these are the performance requirements in the building code. You've essentially got these provisions here that at the end of the day is all about fire resistance and stability, compartmentalization and openings and protections. This is where it says, I don't care how you achieve it, as long as these things are met. And then underneath that, you've got the DTS or the performance solution as well. So the performance solution, it is a pathway to achieve these performance requirements as well. But a lot of today, we're going to be focusing on the DTS from a FRL perspective, and then sometimes it's unavoidable when you go to exposed timber, the performance solution from structural fire design becomes critical. So a few questions. Can I expose the timber, and what is the FRL of the mass timber product? Before we get into that, it's always good to know the different classes of buildings, or the types of buildings. So as you actually require higher fire resistance and as the building risk increases, it could be the height of the building, for example, or the building type. What you need is type A construction, and that determines can you expose it and what's the FRL and questions like this. Through to type C construction is pretty much like a residential building, very low risk, expose your timber, no problem, she'll be sweet. When it comes to an FRL, there's a few different things. So there's these lines denoted by, say, FRL. So firstly, you've got structural performance, integrity, and insulation. So firstly is the adequacy, structural performance. So that's one of the objectives required for the building code. Does it stand to meet the amount of time required? Integrity, are you actually passing through fire and hot gases? And third is insulation. Is it heating up beyond what's satisfactory? And if you look at the different building elements, it's pretty self-explanatory that a column, you only care about adequacy. You're not separating anything. But if you go load-bearing wall, it's adequacy, integrity, and insulation. So in the building code, there's different classes of buildings. It's essentially by the class of buildings. Could be class 5 office buildings, or 9 or 8, which is resi. I sort of maybe getting a bit rusty on my memory there a little bit, or the maximum size of buildings as well. So if you've got an industrial building, a tiny industrial building, no problem. Big industrial building, you need type A construction. And then following that, once you know the type of building, you can actually look at the individual elements, external walls, columns, whatever it might be, to determine what the FRL of the individual element is. Then the next question, can I expose the timber? So in the building code, it says in a building that is type A or B, that where it needs to be non-combustible, you actually need it to be designated non-combustible. I'm not going into detail in this right now, but it's essentially plasterboard or other products that can essentially be classified equivalent by an accredited testing laboratory at the end of the day. But essentially it says external walls and common walls and non-load bearing walls, you need actually to be non-combustible. So that's where it delineates that. It says no matter what, you need to be non-combustible. But what about floors and everything like that? That's actually not covered in C1.9, but it is here. It says anything that touches those external walls is deemed inheritant, and it needs to inherit the same FRL. And that's essentially where a lot of the building elements end up needing an FRL at the end of the day. But if you go through it, it's pretty funny if you actually go through the letter of the code. Now, what I'm going to tell you now, I don't think it is the intent of the building code, but if you look at a building like this, 25 King Street, part of you might says, yep, of course it's a performance solution. Everything needs to be covered up in plasterboard to be DTS. But if you actually follow it, there's a funny loophole here where this could be a DTS building. Again, don't quote me this and sue me or anything like that, but essentially, as it says in the building code, external walls need to be non-combustible. There's no external walls here. Then it says all the floors that inherit it as well, essentially. So class C, it's not this building. Class A and B, there's no load-bearing internal walls as well, but the external wall needs an FRL as well. So if the external wall needed an FRL, the rest of the building inherits that. But then it also says that if you get wall wetting sprinklers, you don't need that to be non-combustible. So that eliminates the external wall, then anything that inherits that. All of a sudden, you've got a fully exposed DTS building. Probably won't fly because it's not the intent of the building code. But again, it's worth knowing how it all works. The second question, how do you achieve the FRL? So this is where you go to Schedule 5 in the building code. There's different pathways. So one pathway is essentially Table 1. Tells you pretty much concrete of certain thicknesses can meet the FRL. There's no CLT or glue lam there. Secondly, if you could do a standard fire test by accredited testing laboratory, which is like a NATA accredited lab, essentially Jensen Hughes / CSIRO, anything like that, they say it achieves the FRL based on a fire test, then you're sweet. C, another one is if it's a minor deviation, but basically the accredited lab is making that call, it's all sweet. Then D, in the AS1720 Part 4, so if it's listed in here, it's actually you can achieve the FRL. So that means things like glue lam, it's got, as long as it achieves this manufacturing grade, then you're totally fine. But also structural adhesives. So you got to check if the supplier's got it, but maybe the supplier's got certification of whatever the adhesive is. But if that's the case, then you can follow char rate provisions in the AS1720 Part 4, and then you actually meet the FRL. E, standard fire test confirmed in a report as well. And this is sort of where it sort of explodes and you can open it up and there's a lot more interpretation here, essentially where you don't need the lab, but you need suitable evidence, basically, to do the job. So if you look at different things, you can imagine you've got a CLT slab, AS1530 Part 4 test to get a DTS. The CLT suppliers now give you char rates to do that, and there's good reason for. CLT penetration to services, 1530 Part 4. The beam, you might get AS1720 Part 4, and same with the column as well. Then the joints and the connections, you also need some testing of the product as well, or equivalent to make sure you're achieving that as well. So with that said, that's a little bit about CLT fire design and broader fire design and compliance. And with that said, now Wendrad, my friend, I'm going to pass over to you. And then at the end, we'll take some questions.
Thank you, Adam, for passing it over. Okay, so hi, everyone. Thank you for joining. My name is Wendrad Bashada. I'm a structural engineer at SPEC Toolbox, Addis Ababa. So today we'll talk about the CLT fire design using the new Eurocode 5. And I will show you how to use a SPEC Toolbox to do this calculation on a live demonstration. So on today's session, we'll cover these 4 things, including fire mechanics, where we see how fire actually works. Then we'll see the timber in fire. And here we'll see how timber performs when it's exposed to fire. And the third, we'll cover the latest Eurocode 5 updates. And finally, we're going to have a live app demonstration for a selected project. So this is fire mechanics. It's all about fire, not a timber, because we need to understand how fire works before we understand how it attacks the structure. So generally speaking, fire is not a substance. It's what happens during a chemical reaction called combustion reaction, where fuel like timber or gasoline meets with oxygen, and there is a reaction like bonding. And during this reaction, energy is released in the form of heat and light, and that's what we call a fire or a flame. So this is the typical general formula for the fire chemical reaction or combustion reaction. One thing we need to take into consideration is fire is not an event, it's more of a process. So on the next slides, we will see the major phases on the fire development process. So the first stage on the fire development process is the incipient stage. Here we don't see any flame, it's more or less a smoldering combustion reaction, and the temperature marks between 0 to 200 degrees centigrade. So with enough supply of fuel, we will proceed to the next fire growth stage, which we call it the growth stage. Here, the temperature rise between 500 up to 1000 right at the flashover. As long as fuel supply is provided, we will pass to the next fire stage, which we call it the fully developed fire. This is the most dangerous fire where every codes are concerned. Here fire reaches the maximum intensity and the temperature stabilizes. This is a more ventilation controlled fire development stage. We don't need enough fuel as for the fire developed state to continue, but if the ventilation is interrupted, we'll proceed to the next fire stage, which we call it the decay stage. Here temperature decreases and the fire weakens, and fully the fuel is consumed, and this stage is controlled by the fuel supply. These are so the very major fire development stage that we need to consider while we are designing members for fire. The other thing that we need to discuss under fire mechanics is the fire severity. This is a measure how destructive is a fire to the structure. This will be measured in terms of the fire's duration, and it will be compared with the fire resistance. So our structure, whether it sustains or not this fire, will depend by the comparison of the fire severity with the resistance provided, and we decide whether the structure pass the verification or not. So now it's all about timber in fire. In this section, we'll see that timber is a fuel and at the same time the structure itself. Unlike timber, steel and concrete, where we don't see burning of the structure, timber is genuinely burned. It's part of the fire that we need to protect, and at the same time, it is a fuel that contributes to the fire development. So this is critical while designing structure to fire, particularly made of timber material. At a micro level, we see the following chemical reaction on a timber. When the temperature ranges between 0 to 100 degrees centigrade, we'll see a drying reaction where moisture leaves from the timber and the timber starts to dry and gets intact. Then around the temperature of 150 degrees centigrade, there is initial decomposition. Here, irreversible reaction starts. Then we go to the pyrolysis reaction. Here, gases starts to escape. At this stage, the strength and the stiffness are highly compromised. And finally, we will end up with the charred or carbonation chemical reaction between 270 to 350 degrees centigrade. Here, all the strength and the stiffness are gone. And at a macro level, timber can be classified into three different layers. One is the char layer between 500 to 700 degrees centigrade. Then comes the pyrolysis zone. Here is the heat affected zone, but the timber is not yet charred. And the other is the unburned wood. Anything below average of 200 degrees centigrade, full strength and the stiffness are retained. And the key and critical parameters that we need to consider while we design members for timber members for fire is the charring rate. This parameter measure how the fire chars the timber. So it's all more or less the rate of the charring. This parameter depends on the species and the density of the timber. So denser and heavier species will char slower, and higher moisture content will slow the charring rate, and also corners will char faster than the normal flat soffit of the timber member. Generally, we will follow the following charring rates for softwood. It's 0.65 millimeter per minute, and we will have different charring rates for different species of woods. And here, this is the most interesting part while we discuss the charring of timber. You know, timber, the charred layer starts to insulate the unburned section when it is exposed to fire. So self-insulating property of the timber that needs to be considered on our design. This advantage, we don't get it from the conventional steel and concrete buildings. So while we design for timber in fire, we need to consider the self-insulating effect on our design. And the other thing we need to consider while we're designing CLT is the glue line integrity. CLT is not a solid wood, it's more of a layered by glue, layered together by glue. There are different adhesive types that we use to glue each lamellas. One is the fire resistance adhesive type. Here, the adhesive or the bonding agent is good enough to resist the fire, and it will stick all the lamellas together even after burning, whereas the thermoplastic adhesive types will fail to hold each layer when it's exposed to fire. As you can see on the screen, the left side is the thermoplastic type, and when it reaches around the glue line or the bond line, it starts to delaminate or fall off from the unburned section. Here, since the fire adhesive type is fire resistance, and it starts to stick what is below or what's already charred. Sorry. Then we'll come to the heat affected zone. As you know, when timber is exposed to fire, the strength and the stiffness is compromised. Obviously, the charred part, we don't have any stiffness and strength, but the heat affected zone is the section where we have a reduced strength and stiffness. And for the uncharred section, we consider the strength and the stiffness are fully retained. So this we need to consider while we design our structure. Now we will go to section 3, where we design timber for fire using the latest Eurocode 5. As it has been discussed by Adam on the design goals, the latest Eurocode provide 3 approaches to make sure our timber structure is safe during fire design situation. There are three solutions, including the acceptable solution, the approved calculation method, and the performance-based alternative design solution. We'll see this in detail. It's already covered on the latest Eurocode 5 under chapter 6, 7, and 8 respectively. So the first solution is the acceptable solution. Here we don't do any detailed calculation. Everything is already provided by the code. We want to make sure our standard simply fits what is listed on the tabular data of the code, and no engineering judgment is required. No charring calculation is need to be done. So this is the fastest path when we need to comply with the fire design code. And if you're building matches, you can use the table provided under chapter 6 for tabulated design data. The next solution is the approved calculation method. Here we use an approved calculation formulas. So there are detailed calculation method. This is the main body of the code. It is not provided on the annex. So you'll see the charring rates, different fire design method, including the effective cross-section method, the separation function method. And we'll also cover how the timber affects the timber species, thickness, and protection level affects the design process. And our calculator, SPEC Toolbox, operates on this method for the moment. And the other design solution is the performance-based design solution. Here, the fire engineer starts to develop all the advanced calculation based on the first principle of the design goals. Thermal and mechanical modeling is required, and you can do it with finite element analysis. The detailed provision is presented on the annex section of the latest Eurocode, and most importantly, this requires a fire specialist to do the performance-based design approach. So now we will see the components of fire resistance. This is more or less similar across all standards and codes. So there are three fire compliance or resistance requirements. The first is the structural adequacy. Here we make sure that the load-bearing capacity is retained during the fire exposure time, and it is measured in the fire exposure time. So R stands for the fire resistance level of structural adequacy. The standard fire exposure times are 30 minutes, 60, 90, and 120 minutes. So we will make sure that the structure will not collapse during these fire exposure times. The next is the integrity. Here we only make sure that the passage of hot flames and smokes to the unexposed side, so that it is convenient for the user to use the fire unexposed side during fire attacks. So this will be measured also on time. This includes 30 minutes, 16, and 90 minutes for the standard fire exposure. And the other fire resistance component is the insulation. Here we limit the temperature on the unexposed side, so the user feel comfortable when using the unexposed side of that structure. So this is also measured with time duration. We will see this in detail on our calculation. These are the typical requirements. Load-bearing wall and floor assemblies are expected to satisfy all the compliance requirements of structural adequacy, integrity, and insulation, whereas partition doors and glazings might require one or two of the requirements for the fire resistance. On the latest code, there are two charring rates are provided. The basic charring rate, here is a fixed number. It only depends on the species type of the wood. And the notional charring rate is the factor charring rate based on the different factor, including the gap factor at a joint and the protection factor, depending on the provided protection type. These are the typical charring rate according to the code. So we will pick what fits for our selected timber species. And then we will calculate the char depths for different phases using the following formula. We'll see the detailed phase that we need to follow while using the latest Eurocode charring model. So there are different phases, including phase 1, 2, 3, 4. So the charring rates can be calculated with the following formula. Beta naught is the basic charring rate. Kg is for the gap factor. K2 is for the protection factor. So depending on the phase, the formula will vary as shown here. This is typically applies for plane member, including CLT ceilings and CLT floor. On our calculation, then comes the charring phases for the European char model. On the latest code, the char model classifies the charring framework into two major classes. One is when the timber is initially unprotected, and the other is when the timber is initially protected. When it is initially unprotected, the charring rate follows phase 1 charring phase, where we don't have protection. And for the initially protected cases, we're going to have four charring phases, including the encapsulated phase. Here, no charring occurs at this stage, so phase 0 is denoted with no charring. And phase 2 is a protected charring. Here we will see charring of the timber behind the protection, so the protection is not failed, but charring already started. Then come post-protected charring. This is the charring stage when the protection system fails, but the charring starts to speed up with a faster rate. And then comes the consolidated charring phase. This is typically above, for a thickness that extend above 25 millimeters, the charring rate will start to slow down. That we have discussed as a self-insulating behavior of timber. These are the major times that we need to consider on our charring calculation. So the first one is the starting time of charring. This denotes where charring begins. So if you have a protection, the starting time of charring will be delayed, and we will calculate it with the following formula depending on the protection type that we used for the floor or wall buildup. The other is the failure time of the protection. Sometimes charring starts behind the protection before the protection fails. So we need to have to calculate at what time that protection will fail, and also the consolidation time. This time corresponds to the charred depth of 25 millimeters. So we will calculate at what time the charring depth reaches 25 millimeters. These are the critical time that we need to consider when calculating for timber in fire. The other is the zero strings layer. This is a critical one. As timber is exposed to fire, a portion of the timber will not fully charred, but it is affected by the heat. So we need have to deduct from the uncharred thickness, so that this thickness is dependent on the char line or where the fire stops. So if it is the first layer, we use this row, and if it is on the other layers, with the second one. And it also depends whether this is for the floor, whether it is a tension or compression side of the floor. And it also depends whether it is initially protected or not. So we will follow this table for the floor. Likewise, for the wall member, we will follow the following zero strings calculation formulas. These are totally new, based on as compared with the current Eurocode 5 for fire design. So the following 4 slide will show us how timber chars based on the European model. So depending whether the bond line holds the charred layer or not, we have different framework. So this is for bond line integrity is maintained. So if the member is initially not protected, we will use the charring model shown on the left side. If it is initially protected, but the starting time of the charring and the failure time of the protection is different, we will follow the right side charring framework. These are more or less a blueprint that we need to follow when we calculate the charred depths while using the latest Eurocode 5. Then comes if initially protected, and also the starting time of charring and the failure time of the protections are equal. So we will follow this one. if the starting time of charring and the failure time of the protection are also equal, and also the time at the consolidation is the depth at the consolidation time is less than 25 millimeter, we use this plot for our calculation. The same applies when the glue line is not maintained. That means if the bond adhesive will not support a higher temperature, we will follow the following detailed framework. This is for initially unprotected, and this is for initially protected, but the timber, the starting time of charring and the failure protection times are not equal. And the same is true for initially protected, with timber charring time and the failure protection time are equal. And when the consolidation time is at a depth less than 25 millimeters. So we need to strictly follow these charring frameworks while using the European char model for calculation of the char depths. Now we will see a little about the design method that are provided on the latest code. So the simplified design method, here we will calculate the remaining unburned thickness of the timber using the following formula. D effective calculates the effective charred depth, and H effective is the unburned or remained section after the fire. So this plot and dimension applies for one-dimensional charring, where when we design a plane member including floor and wall. And this one applies for two-dimensional charring when we design timber beam and column for a fire structure. The other is the separated function. So under separated function method, we will see the integrity and insulation criteria is met, and fire can have different heat flow paths. So as you can see, the red dotted line shows the different fire or heat paths. So we will calculate each by selecting which one is the critical, and for our design, we will use the envelope of all possible heat flux paths. So this is critical when we select our floor build-up or wall build-up for the fire design using the latest Eurocode 5. The other topic that we need to discuss is the protection time. Here we calculate individual layers protection on our build-up. To calculate the individual layer protection, we need to account the following parameter. Here is the basic protection times. So the code provide generic formulas for the default protection types. There is also exposure factors for the exposed side, and also an exposed side factor. This will affect or factor the basic protection time. Then we have a correction time or the additional time, and also the joint factor that we need to consider. So with this all formula or calculation, we will decide the protection time of a single layer on our floor or wall build-up. Likewise, for the insulation time calculation, we use the sum of the individual protection time plus the final layer insulation time for the calculation. With this, now we will proceed to the app demo. Before proceeding to the app demo, I will try to brief you the project. This is a 6-story mass timber building that we will use for our design. It's located in Brisbane, Queensland. We will use a design standard of AS 1720.4. And for structural system, it considers the CLT floor, CLT wall, CLT beam, and JLT beam and JLT braces. And also we have JLT columns. For the fire design, we will use the simplified design method, and we will follow using the SPEC Toolbox calculator. This is the typical floor of this building. So we'll have a load spanning in the X direction or in the lateral direction. The support is the beams, and when it comes around the core, the support will be the wall marked by the red color fill. So we will design a selected member. So for the structural system, our floor is 118 millimeter thickness. It's 6 meter by 8 meter span. The same is for the wall, and the JLT beams are with the following dimension, and we have a bracing at axis A, I, and at axis 1 and 4. With this, we'll start to calculate the loading on the floor. So we selected a one strip span for the analysis. And as you can see, the highlighted here, one strip width, 1 meter strip width is used. The selected CLT type is a CLT KLH with 5 layer and 180 millimeter. The superimposed dead load is 2.75 kilonewton per meter square, and the live load is 3 kilonewton per meter square. For this section, we will try to verify the structural adequacy or load bearing resistance for 19-minute fire exposure and insulation for 30-minute fire exposure. So with this, we have two options for the floor, first floor up to fifth floor build up. The first build up is we have 5-layer CLT and then followed by wood fiber insulation and a gypsum plaster board of 30 millimeter thickness, and the wood fiber is 50 millimeter. The second option is the one protected from underside with 2 layers of gypsum plaster board. Still, we will have a 50 millimeter wood fiber insulation between the CLT and the gypsum. So the first option is economical. We will see whether it satisfies our design, and the second option is it's an enhanced protection system. So now let's proceed to the SPEC Toolbox app. I have already built the calculator. I already created the calculator, so we can follow to save time. The first thing that we need to define is the region. So I set the region to Australia. We will define the build up. This time the supplier is KLH and the 5-layer and 180 millimeter thick CLT floor. Then we set the design code and also the analytical method. The analytical method is extended gamma method. If you like to see the detailed information, you can click on this little blue button so that you can have a detailed information about the input that you are going to define. Here we have the design factor for the Australian code. Then comes the loading data. We want to calculate the loading combination using the default load combination as per the following loading code. And we will set all live load factors and also the creep factor. This is important because we need to define all necessary input for the ambient section before we proceed to the fire calculator. Then comes the analysis section. As we have seen on the presentation, it's a 3-span with 6 meter each, and the assigned load includes the live load of 3 kilonewton per meter square, which we define it here in the dead load is 2.75 kilonewton. This is superimposed dead load, and the calculator will do the self-weight calculation automatically. So we set it yes. If you don't want to include the self-weight calculation, you can set it this to no. Here is how we define the span. We have 6 meter for each, and also the support condition. So this will be our system. Now we will define here the deflection data. So the deflection limit or criteria can be defined here, and also the vibration data or input data for the vibration analysis method. Here is also defined. For the moment, I have selected the FP innovation with a vibration improvement of 20% increment. So on the output section, you will see the output summary first. This is how each and every major verification are checked. So deflection, vibration, shear, and bending are passing for the ambient case. Now we directly proceed to the fire input data because our today's session focus mainly for the fire data. So by default, when you open CLT floor or a wall, you have this new tab, or you can also add the calculator here. So the fire tab will present like this. This is our end result on the fire charring. Let's see the design inputs for the fire char before that. So the fire method, as we have been discussed earlier, it will be the latest Eurocode 5. We also have different methods, including the standard test and the current Eurocode as per the Austrian National Annex. But on this example, we will focus with the latest Eurocode. For the performance check, we will see the load bearing and insulation. For the moment, integrity is not included, but load bearing and insulation already implemented on the calculator. This is all about how the dynamic plot displays. So if you want to see what is the remained section on the flexure on the top intention side and topping compression, this entirely controls the display. It doesn't affect your calculation. Then comes the fire data. So we set the load bearing fire exposure time to 90 minutes, the insulation time to 30 minutes, and the charring rate can be taken from the latest Eurocode. The supplier of the CLT can provide this charring rate, or we can do a manual input, but for the moment we stick with the latest Eurocode. Here we decide whether the glue line is maintained or not. For the first case, we set the glue line integrity is not maintained, and the fire is exposed from the underside. Since the fire duration is a little longer, so we need to provide a protection. Before that, we define the factors that account for the protection of the CLT. This comes from the test data, so we set it here 0.7. We don't have a joint at the location that we are studying, but if you have a joint, you can define different joint types for the CLT and also for the protection system. Here we will start to define the protection from the underside. So if you set this, the timber section will not be protected, but if you click here, you will going to provide a protection from the fire exposed side. So now fire is exposed on the underside. These are already defined. So we have a wood fiber cavity insulation with 50 millimeter thickness, and the protection factor K2. This is taken from the test data, and we don't have a joint at that specific heat flow path as we have seen on the separation function. Then comes the external layer, which is the gypsum plasterboard. This time we have type A 1 layer, and the thickness is 30 millimeter. So this will define the entire data for our calculation. As you can see, shear and bending verification are passing the requirement, that is the load bearing requirement or the load adequacy or strength adequacy requirement is already satisfied, but the insulation performance is not, because the efficiency exceeded 100%. So we need to do a thing here, because the system is not supporting our load during a fire situation. So this is option 1. Now we go to option 2, build up. As you recall, the only thing that we change here to make the system efficient is we set the gypsum plasterboard 2 layer. Previously it is 1 layer, so we have equal thickness for these 2 layers. As you can see, the dynamic plot thickness also changed for the timber section. So the string is verified, and also the insulation requirement is verified. All checks are passing because our gypsum layer is 2 layer. So let's see what are the reports on the charring calculation. We will report the charring rate factors, so the factors that we need to use for each layers on the build-up, even including the CLT member itself. So the gypsum plasterboard, the wood fiber insulation, the CLT, all basic or the basis parameter will be presented here. Then comes the K3 factor. This factor is for the CLT. So since this time it's a floor, we will use a K3 factor 2.0 that accounts for the post-protected charring. Then comes the gap factor. This factor defines on the joint dimension that we have. So this factor is now set 1 as per the code. And we will see the charring rates, the initial charring rate and the notional charring rate for initially protected and the glue line integrity is not maintained. So the basic charring rate and individual phases are calculated here. Then comes the zero strings layer depth calculation. So the floor, for the floor, using the tabular data from the latest Eurocode, we can calculate the individual cases for the zero strings layers. So for the tension side and the compression side. The other is the protection time. So as we have discussed earlier, the starting time of charring, the failure time of the protection, and the individual protection time need to be calculated in detail. So this is the way how we calculate individual layer protection, including the CLT and the protection system. We include the CLT when we study the insulation, but for the starting time and the failure time of the protection, we only consider the layer prior to the CLT member. So here is how we calculate the insulation time. So everything is presented in detail, and we will see the utilization for the insulation. So it's below 100%. So we are safe. And these are the protection failure time. So this is calculated using the latest Eurocode, and also the starting time of charring is also presented here. This time, both time are the starting time and the failure protection time are equal. And also the consolidation time is also calculated here for the bottom side. And finally, we will present the final design thickness. So this design thickness is calculated using the simplified design method. So these are how we present individual calculation. This is the thickness of individual layer before fire, the charred thickness, the zero strings layer, and the final effective charred depth. And finally, we're gonna have the unburned thickness post-fire. This is for the tension on the top side, and when the top side is in compression. So this will be the detailed report. On the other tabs, we will see the panel property calculation using the selected analytical method. This time it's a gamma method. We'll see all detailed calculation, the AI effective and the static moment calculations for bending and the shear strength calculation. Then comes the loading calculation. Here it follows the load combination rule of the selected loading code, and the analysis section. Here we will see the detailed analysis result for the selected load combination. This one is the shear force, bending moment, and the reaction force for our span. And you can even see selectively for a specific load case. So if you like to see only the self weight, you can hide the rest load cases. So every data is presented on the analysis section. And finally, we'll go to the design section. Here we see the bending design as per the Australian standard. So the design utilization or efficiency is around 40%. So our design passes. The same is for shear design. We will verify the shear capacity using the latest Australian code, and it's around 24%. So both the bending and shear verification are satisfied, and the integrity, the insulation requirement for the fire performance is also satisfied. This is how we detailed calculate for the floor system. You can save your calculator and have a printout right here. So now let us see the wall section. Before that, we can see from our detailed calculation what is left from the option one will not provide the required performance for insulation. That's why we skipped for now, and we take option two or option two build up for our floor from first floor to fifth floor when fire is exposed from the underside. These are the typical data that are extracted from the SPEC Toolbox calculator. So from this, we can see that the charring depth is calculated, the residual section is also verified, zero strings layer is included in detail, and the bond line integrity is also mentioned. The design output shows us the required fire rating is satisfied, the fire protection govern our structural behavior, and option to provide the detailed performance for strings and insulation. So we stick with option 2 for our system. Now we will go to the wall along axis D for the wall fire design. So this will take a load from upper floor and also from the floor that's going it support. So it's located along axis D. We do a load taking down here. The reaction from the floor analysis is presented here along axis D. So we sum up for the above five floor and the 4-story walls. So this is the total superimposed dead load, and the live load is 36 kilonewton meter. This is calculated using the following formula. This is unfactored load. In the fire, this time the fire requirement is 120 minutes. As you can see here, we are required to have a fire from the left side because the fire, the right side is lift shaft, so we don't expect that is the fire side, and we are aimed to protect the inside of the lift shaft is not exposed to fire and insulated fully. For the wall build-up, we will have also two options. The one you see on the left side is still the economical protection, where we only have one layer of gypsum plasterboard with 30 millimeter thickness and along with wood fiber insulation. But for the second build-up, we have two layers of gypsum of 30 millimeter thickness and a wood fiber insulation in between the CLT panel. So let's go to the app and see how the wall fire is calculated. So again, we start with the ambient section that says structural tab here. So we'll define all the necessary material definition, the CLT supplier, the layup. This I have already stated initially, so we can see what is inputted here. The design methodology set to Australian standard, the design code data. What is new on the wall is we define the eccentricity of the load from the above. This time I set this value to 100 for the ambient case. For the loading data, we'll have dead load and live load. We'll set the load combination here, and the factor are also presented here. The self weight of the wall is also calculated by the tool. And finally, we'll define our calculated line load on the wall, which is 58.4 kilonewton per meter of superimposed dead load and 36 kilonewton per meter live load. The self weight of this specific story will be calculated by the app. These are the analysis data. We use a shear analogy for the AI effective calculation. Intermediate restraint is not provided, and the shear factor is also defined here. The height of the wall is defined as 3 meters. So you can see on a dynamic plot here, this is the top view and this is the section view, all the data that's defined for the wall. Now you can also verify all output summary for the ambient section. Here we check the compression, the bending, and the combined effects. So all requirements are satisfied for the ambient section. So we simply move to the fire section or the fire tab for the calculation. Here we'll define the eccentricity data for the fire specifically. This time it's 20 millimeter. We set the fire method as we have done for the floor calculator. We need load bearing and insulation performance check, and then we have the fire resistance to 120 millimeter, and the insulation is 16 millimeter. It's a more strict time duration as compared to the floor system. And the basic charring rates and glue line integrity are also the same as we have set for the floor fire calculator. And the fire is coming on the left face. You can define the fire from the right face or from the both phases of the wall, but this time it's from the left side, and you can define the protection for the left face as we did for the wall. So the left side protection includes the wood fiber insulation and the gypsum plasterboard. Here are the thickness and also the joint type data. If you have a joint for that specific protection, you can define using the this drop down, and the specific joint types are listed here. For the moment, we don't have a joint type for our case. As you can see on the first option of the build up, the strings requirement is not satisfied. This is critical. That means the load bearing capacity is compromised. even if the insulation performance is satisfied. So to make sure this checks work, we need to proceed to option 2. Under option 2, what is new is the gypsum layer is now two layers of type A. So every input data is the same, but the gypsum thickness is the gypsum layer is 2. So for this updated input, our calculation for strings design is working now well. So the fire compression, the fire bending, and the fire combined effect is working along with the insulation performance requirement. On the charring tab, we'll see the detailed data for the charring of the wall panel. So including the basis data, the factors for charring rates, the charring rate calculation, the zero strings section, and also the protection time calculation. So we will see the detailed protection time and the insulation time calculation and its utilization. And we also have the failure time of the protection and the starting time of the charring. This shows the detailed calculation. And finally, we're going to have the final design thickness for a wall. And this is presented here, what is left on our section. So with this, we'll proceed to our presentation. So what is left after fire is the following one. So the dark brown is what is entirely charred, and the light brown is what is deducted as a zero strings layer. So from the two options, we can see that the less deducted section is the option 2, and we'll select this for our wall at the specified story, or that's a second story. So with this, the wall loading is verified on our app. The charring model is applied, residual section calculated, the fire resistance is verified, and the design output shows that the structural adequacy, integrity, and insulation are satisfied. So from today's presentation, I will consider these 4 things that you need to take with you. The first thing is fire is a process. That's why on our detailed calculation time matters. So we need to consider this nature of the fire. Timber chars predictably until it reaches the bond line, where we consider integrity of the bond. The latest Eurocode publishes how it treats the CLT floor and the wall in detail. This is not provided on the current Eurocode. And finally, integrating or using the SPEC Toolbox, you can use the European char model in order to calculate the remaining char thickness and the design of the member during a fire situation. So this is from me for today. Thank you everyone for your attention.
Thank you so much, Wenderad, and well done again, and congratulations on, because I think everyone watching this webinar can imagine the amount of permutations that the new Eurocode has to get it all right, basically. And we also have Anto on the call, who's the lead software developer on it. So congrats to our team. So we've got some great questions. So firstly, we're going to start with, I'll do a quick compliance ones, Wenderad, and then there'll be more of a detailed questions as well. So Andrew asked 2 great questions in Australian context compliant. So where does the plasterboard layer performance come from? Do manufacturers like CSR provide this performance, or is in this demo, is this from the Eurocode? So yes, we did focus on Eurocode today, where you've got the individual protection methods out of Europe. So that would be performance-based solution in the latest code. In the existing code, I believe it's like you've got to pass the 300 degrees test of some description for 30 or 60 minutes or something like that. But judging by your second question, I feel like you probably understand the building code yourself. So your other question was, is it likely that CLT in typical commercial buildings will be unable to provide the insulation performance? My intuition says usually it'd be fine. That wouldn't be the governing factor. But yeah, the new European methods yield interesting outcomes there. But yeah, great question, Andrew. And I'll take that as a general comment for everyone to read. Then I'll take one more, then Winner, I'll pass the one finally to you. So how would you recommend using design codes for European suppliers? Is it okay to mix and match vibration and fire? So we generally say European suppliers using European methods as best you can, and then Australian suppliers, you may use Australia where you can and borrow from Europe where not. potentially. But finally, Wendrad, final question for you, man. We got, does the new Eurocode provide any guidance on connections and joints design from a fire perspective as well?
Thank you, Adam. That's a very important question. Yes, the latest Eurocode 5 provide a detail on how to design a connection for a fire. This that we are building on the current stage, and it will be on our app in the near future. But it has a section that deals about connection in fire. Yeah.
Got you. Great. We've got a question here. Someone wants to explore, get around the non-combustibility requirement. Jacob, I'd say speak to a building code consultant, and a CLT suppliers would probably be the best one to support there. Andrew Dunn, shout out to him. That we don't want to use loopholes, but he's sort of, if you know Andrew Dunn, he's very helpful at understanding the building code and everything like that. But yeah, great. And really appreciate the comments, and you're getting a bit of love in there, Wendrad, from everyone, because you've done a great job basically for everyone in making it easy to design fire at the end of the day. So just to wrap things up, it's worth mentioning the good news is we've covered structural fire design today. We are going to start doing passive fire systems on SPEC Toolbox. We're working with Imran, who's a bit of a powerhouse in ANZ as well. And we actually got our first passive fire systems provider signed on the app. So that's something we're building similar to sort of streamline compliance there as well. It's worth mentioning, last webinar was on the shear wall. We're still just doing final QAs before we release it. We're improving our internal QA systems, but the shear wall calculator is really off chop. So excited to share that. That'll be next week. And then the hanger module, similar thing, like late stage QA. We're improving our QA process. It just means things take a little bit longer. But probably the big news is we are working on the completely overhaul of pretty much the whole app, where you're going to have a much better user experience across everything, finding what you need essentially, and pretty interesting and useful AI integration, particularly from an active perspective. So, this is failing, and then click a button and then it'll actually optimize the design one click. So that's sort of interesting looking things. And yeah, finally, our next webinar is going to be on the 3rd of September. You may have noticed we've done acoustics design in mass timber. The general direction we're heading is to sort of integrate the acoustics over fire and structural, so you could actually have a full system design in one place, because that's sometimes where a lot of the complexity goes. So with that said, thank you so much, everyone, for joining on today's webinar. We hope you have a great day. Reach out if you've got any questions, and SPEC Toolbox, it's there for everyone to use and get your hands dirty on. So thanks so much. Have a great day, and we'll end the webinar there.